Hi, I'm Phil, and today we start our second week of microbit and electronics. And this week we're going to look at microbit and Tinkercad, and we'll use Tinkercad until the Grove electronic devices in the Bit Gadget kit come along to the school. And we're going to do quite a few projects, including this one on my desktop, which is monitoring to see if the bins are full or not. And here I've got on the right bin 1, which monitors if the bin is full, and if it is full, it sends a radio message to the bin master by microbit radio. Okay, so the objectives are to look at electronics and compare electronic circuits with the equivalent microbit-based circuit. We're going to build electronics with microbit, and that goes beyond what we did last week, where we only built the electronic circuit. We'll simulate the electronic circuits, including simulating the behavior of microbit, and we'll learn how to communicate with microbits from one microbit to the other microbits. And in the real school playground, we will use a different form of communication called LoRaWAN radio. We'll have a look at how we can use debugging with the serial port to explore our make code. And we'll get to know the Bitmaker and the Bit Gadget kit once they arrive at the school. Okay, so last week I introduced the beginner's guide to circuits from Dole, and invited you to get the book and build the circuits and find out how they work. And we will use this as the base for this week. Some of the circuits will be alternatives or use some of the same concepts in these circuits. So in the circuits that we've got, they're all available on the Tinkercad Classroom. And if you've read the book and want to explore the simulation of the circuits, go across to the Tinkercad Classroom. And these are the circuits that I will be exploring later with microbit. Okay, so we'll be using microbit and simulating the code and electronics on Tinkercad. So what's new compared to last week is setting up and connecting microbit, and also doing some coding. We're going to do a couple of projects. One is the name badge, and another one will be to look at using a push button, an external push button, and turning on or off an LED, which is also external. As a stretch project, you could transmit your name to the rest of the class. So this is an extension of the name badge, but you use microbit radio to send your name to the class. And an additional project is to detect a full rubbish bin with the microbit and a photoresistor. And this is not the only way to do it. When you get your Bit Gadget kit, explore other ways and more reliable ways of doing this. And finally, an additional project would be a quiz program where you could get the microbit to manage a quiz show and keep the scores and allow students to identify rubbish and which bin it should go in. Okay, so in the name badge, I want you to program the microbit, and later we'll hook up the circuit. So in the name badge program, we'll make it quite simple. We'll won't add any electronics at the moment. So the requirements are that when you press button A on microbit, it will show and scroll across your name. And when you press button B, it will show your surname. And just to make it a little bit more interesting, if you shake microbit, you can send a different message. And the process we go through with this project is like all the other projects. We get to understand the requirements. We know what they are. And we'll come back to those requirements after we've done our testing to make sure we've met the requirements. We do a design. We then construct, we build the hardware and the software. And then we test it to see what the results are and check them against requirements. And at that stage, after you've done it all, you might find bugs that you have to correct and go through that cycle again. Or if it all works and you're happy with the results, you might even be able to suggest some improvements or extend the requirements for a new project. Okay, so the design here is actually quite simple. We just choose the hardware. We're going to use microbit. And the construction for this stage of the project is that we're going to use microbit. And when you press button A, your first name, and when you press button B, you get your surname. And here's the code. So go across to Tinkercad, grab the microbit, and start coding. So there's not much to it. You should be able to get that going within a couple of minutes. Okay, so once you've done that, you've done your first code with microbit on Tinkercad. We're going to explore some of the limitations of microbit. And the main one is that microbit, while it consumes 90 milliamps for version 1 and 120 for version 2, the microbit electronics on board consumes about 30 milliamps. And so there's not much left over when you start adding additional electronics. And each pin on the microbit, that's the edge connector. If you look at the edge connectors on the bottom, you can source 1.5 milliamps, or in the high drive mode, the maximum you should put through a pin is 5 milliamps. Now, bearing in mind, it's quite easy for a external LED to get up to 10 to 20 milliamps. You could be exceeding the maximum current allowed. And not only that, there's an additional requirement. You shouldn't exceed the maximum current of 5 milliamps on more than 3 pins of the microbit. And even when you use the microbit's LEDs, you're adding additional current to the load. So if you have all 25 LEDs on, that's going to be an additional 14 milliamps. So how do you overcome that limitation? Well, one way is just don't use microbit's LEDs. And another way is to use an external power, a regulator's external power, for any additional electronics that you put on to the microbit. We're going to explore using the transistor as a switch with that external power. And later on, with the Bit Gadget Kit, you can use Grove electronics. And when you add more Grove modules, you need to put an additional USB power source for the Grove Bitmaker board. Okay, so using a transistor as a switch, I've created the diagram on the bottom from Fritzen as the schematic that Tinkercad gives you is a little bit crude. And even with Fritzen, I've had to modify the topology so that it's easier to understand. But the basic idea is that the microbit will be used and it will feed in base current to the transistor, and the transistor will switch on the LED here, which is limited by the resistor, so that no more than 20 milliamps goes through the transistor. So while the microbit might have a small amount of current into the base, no more than 5 milliamps, we can have a much larger current go through the collector and the LED. Okay, so what we're going to do is construct another circuit on Tinkercad, and the requirements this time are that when you press button A, you turn LED, the green one, on or off. So pressing the button toggles the state of that LED. And the other one, which is actually independent of the microbit, when you press button A, you turn it on. And when you release the button number 1, you turn LED number 1 off. So here's the circuit. And all you have to do now is go across to Tinkercad and construct that circuit. And you should come up with these components. So there are 2 resistors. There's a red LED and a green LED, 1 push button, and a microbit. And the circuit should look like this on the breadboard. So go across and see if you can do that. And I will release the project on Tinkercad Classroom later this afternoon. So let's have a look at the code. Very simple code. What we're doing is using the digital write pin, both high and low, to switch on the LED, which is connected to port 1. Okay, here's another interesting project. And this time we can also show the current in the base and the current in the collector. And we're going to connect 4 LEDs this time. And if we try to do this with only the microbit power, we would far exceed, because each of those LEDs, depending on the resistor, can go up to 20 milliamps. So with 80 milliamps, we far exceed the maximum allowed current on the load through the microbit. But what we're going to use here is a external power supply, and it will be connected to the collector and the load, which is 4 LEDs. Okay, so here's the circuit, and this schematic comes from Tinkercad. So all you have to do now is go across to Tinkercad and wire up the circuit. So after you've actually wired it up, you might be able to compare it with the one on the Tinkercad Classroom. So this will be available later this afternoon. And here's the software for it. So we're going to use port 1 as a switch. And when we press button A, we turn port 1 off. And when we press button B, we turn it on. And we're going to simulate that state of the LED also on the microbit LEDs. But you might have noticed that I'm beginning to break one of the rules, and that is using microbits LEDs when I've got some external electronics. But we're okay here because we're using an external power supply. Okay, so how much current is used? So you can see from the ammeter, which is connected in series with the base of the transistor, and that goes into the via a limiting resistor. We're got no more than 2.43 milliamps. And the collector current, which is feeding the 4 LEDs, is 25.8 milliamps. And that's been limited by the 470 ohm resistor, which is in series with each of the LEDs. And this also illustrates series and parallel circuits. So we have components here which are in series, and we also have some components which are in parallel. Okay, when you get your bit gadget kit, you'll be able to do this simply with MakeCode. And we're using port 0 as the switch. And when you press button A, you turn it on. And when you press button B, you turn it off. And you might like to have a look at what other ports you could use on the microbit. Okay, our next project, we're going to extend this a little bit further, and we're going to use 2 push buttons and 2 LEDs. So when you press push button 1, it turns on LED 1, and when you press push button 2, it turns on LED 2. And here is the materials that you use for the project, and here's your circuit. So you might like to go ahead and wire this up yourself and see if you can get it to work. So for the push buttons, we're using port 0 and port 1. And for the LEDs, we're using port 5 and port 11. And after you've constructed it, have a look at my result on the Tinkercad classroom. And it's under the name of Topic 2, Button LED 1. And here's the code for it. So we've got a number of blocks, the on start, the forever, and we've got the action or the event buttons when we press the P0 and the P1. And these are used in a similar way to the button A or button B on the microbit, but they're external. And what we're doing here is actually toggling. So the LED state can be toggled. Okay, so how could we apply this to our rubbish collection project? Well, what we want to do here is determine when a bin is full without opening the bin. And we're going to use a light beam, and it's going to be implemented in 2 ways. I'm only going to do one on this video, but you can have a think about perhaps at least one other way to detect if the bin's full. And on the dial circuits, we're going to use the cookie jar project. Okay, so the light beam, you can see that it's on the left with a LED setting up the beam, and on the right there's a light sensor. So when the bin's full, it cuts the light beam. And as an extension, we can use a tilt switch. So when someone opens the bin, it then disables the rubbish detection sensor. Okay, so we'll start off with Tinkercad, and this time we're going to use 2 microbits. On the left, we've got the bin 1, which is a slave for the communications, and it's going to use the external sensor of a light detector, and we're going to use a LED for setting up the light beam. And on the right, we don't have any additional electronics, but the microbit radio is going to be used to scan the status of bin 1. So go ahead to Tinkercad and construct this. But I might warn you that I did have some problems, not with the electronics, but with the coding. And perhaps you can fix that up yourself. So here's the circuit for bin 1. And here's the code for both the microbit code and the master. So there's a little bit of logic there. And in the forever loop, it's turning on the LED via port 0 only occasionally. And we're doing that to save battery power. So we only have to check this, say, once every minute. At the moment, I'm checking this once every 4 seconds using the first block in the forever loop. And port 1, we're getting the analog value there, which is the light value. We show that on the microbit LED. And if that light value is above the threshold, then the bin is full, and we show all of the LEDs to be on. And then we send the message bin full to the master via radio. And if the light value is less than the threshold, we set the bin full to 0, and we send the bin full message via radio, and we switch off the red LED, which is used as an alarm that the bin is full. So if the bin isn't at the maximum, we switch off that LED. And when we've finished that process, and we switch off the LED, which is used for the light beam. And on the right, when we get a message, we set up the bin full, and when it is 1, we then show all of the LEDs. So the only problem here is that we're using the microbit LEDs, and when we're using the electronics, it's probably a good idea not to use it. Okay, so again, here is the code for the bin 1, and here is the code for the master. So you might like to go ahead and see if you can construct that. And the results that I got, that it does work, but only for 2 loops of the forever loop. So the simulation actually crashes, and the code for the microbit radio is defective on Tinkercad. So we might actually look for another solution, and the solution that we're going to look for will use the bit gadget and the electronic Grove modules. So what we're going to do is when the bin is full, we're going to show a red LED on top of the bin, and that will illuminate when the bin's full. And the other microbit will be the bin master, and it's going to cover the grounds of the school. So bearing in mind, we'll only start off with a desktop, and we'll only use microbit radio. So these are the components, and they're all Grove components. We need also microbit. We need Grove components, Bitmaker, which connects to the Grove modules and also connects to microbit. For the sensors, we're using the light sensor and a tilt sensor. And for the actuators, we're using LEDs, a white LED to set up the light beam, and a red LED for the alarm that the bin is full. Okay, an introduction to the Bitmaker. You can see that on the right, we've got a series on the vertical there of the ports, the Grove port, P0 and P1, and just underneath that, P1 and P2. So you can see that port 1 is actually repeated on 2 Grove modules. And for many Grove devices, they're only going to connect to the first one, which is the P0. And when you look at the Grove cable, the first one, the yellow wire on the Grove cable, connects to P0, and the white wire connects to P1. So you can see that we can get up to 6 Grove modules connected to our microbit. And on the top, a couple of things to note, that you need to supply an additional USB power, and that can come from your computer or from a USB power supply. And you need to switch the power on-off switch to on to make sure that you get power. And this way, we're providing an external or a separate power supply for the electronics that's on the connected to the Bitmaker board. And on the left, we've also got 3 Grove ports. Starting off on top, we've got P8 and P14. And there's a special one just under that, and it's the Grove I to C port. So there's a mistake there. It should be I and not 1. And under that, we've got port 16 and port 15. But there's also 4 NeoPixels, and these can be programmed for any color. So it's called the NeoPixel RGB LEDs, and they're on port 13. Now, if you have Bitmaker version 2, there's no buzzer. And the reason for that is version 2 is meant to be used with microbit version 2, which has a buzzer on board. So here's the way that you hook that up. You've got the 2 LEDs. You've got bin 1 on microbit 2, and the master is microbit 1. So we connect, and you have to get the orientation correct. So it should look like this when you connect the microbit to Bitmaker. And we connect the Grove modules. So on the right, we've got the white LED that sets up the beam to our detector, and it goes on to port 1. And we're going to use the Grove light sensor version 1.2. And both of those should be in your BitGadget kit. And on the left, we connect the red LED to port 16. And we're going to use microbit radio. So when the bin's full, not only do we illuminate the red LED, but we also send a message out to the master, the bin master, on the status of the bin. And to connect the Grove modules to Bitmaker, you use a Grove cable. And you won't have this in your BitGadget kit, but later on, you may be able to use the Grove tilt switch and connect that also to the Bitmaker board. And here's the code for doing all that. So you use MakeCode, and I've started off on the top left. I've got an extra module for debugging just under that. The forever loop is the longest one. But on the right, we've got some additional functions, which are mainly used for setting up and compensating if the light intensity from the beam is not enough for considering that it's also picking up not only the beam, but also the ambient light. So on start, we set up the variables and we switch off the LEDs. And we set the radio group. So this helps us with our communication. And we're going to show the bin number. So this is bin number 1 will be shown on microbit's LED. And in the forever loop, I've split this up to a couple. And it's similar to the previous one where we get the light value and the light is on pin 1. So the analog value of the light value is set to the light value variable, and it's compared against the threshold. And if it's below the threshold, it will set the bin full variable to 1. Alternatively, you could use a logical variable, either true or false there. And if it is 1 and it's full, we then set the red LED on port 16 to 1. And we show on microbit's LEDs all of the LEDs. And we set bin full, else we don't set the alarm LED. And in the end, we do something special here. We actually combine the bin number and the bin full status as a single number. So this is a bit of a trick for the radio communications, where the most significant number that is in the decimal is going to be the bin number. And that's why I've only got 9 bins. And the least significant number is the status. So we can send, say for bin 1, a number via radio, which will be 10 for an empty bin. And we send the message 11 for bin 1 full. And we also switch off, the next statement switches off the white LED for our beam. And I've also called the debug statement just to check. So that's not really necessary. And when you're happy with the program, you can get rid of that call. For the push buttons, I can set up the bin number by pressing button A. So if I want to have a different bin number, I can just use this function. And for button B, all I'm doing there is just testing that the white LED is working. So it's not part of the main operation. It's just a fault finding function. And if I press button A and B together, I then set the alarm bit on, then turn it off after 2 seconds. And something special here, if I press the logo, so the logo is only available for version 2 of the microbit. What I'm doing is just increasing the light threshold by 100 units and cycling through that each time I press the logo button. And that helps to compensate if we've got too much ambient lighting. Okay, for my debug, I'm sending information on the bin number, the status of the bin, the light value, the light threshold, and if the bin is opened or closed. All of that information is sent via the serial port, and my Windows PC, using a program like PuTTY or the Arduino monitor, can actually monitor that each time I'm going through the forever cycle. Okay, for the bin master, it's a bit different. Using some of the same variables on setup in the forever loop, when we do get a bin full message, we then show the bin number, which is full, and we play a melody, and we then repeat that cycle. And the special block is on the right. So it's acting as a radio receiver, and it needs to decompose that radio message into bin number and bin full. So a closer look at the on start, where we set up the variables, and we set up the radio group to the same radio group as all the other bins, and we show the bin number. And here's the forever loop, where we give warning if a bin is full, and the radio received process is done here. And I've added an extra one for the buttons, but my forever loop isn't quite complete. The idea here is that the sound message might annoy other students, so you can toggle the sound on flag so that you can switch off the the audio sound if that's annoying to others around you. Okay, so if you want to see what the results are, head off to my YouTube video, Smart Bins Using Microbit, and there's the link for that. Okay, so in the real school playground, we've got quite a long range. And while Bluetooth can get up to 100 meters, and we can even extend Wi-Fi, which normally would be under 15 meters, we can extend Wi-Fi with a Wi-Fi network. These are a little bit complex and not so reliable. So there's a new radio system called LoRaWAN, and LoRa stands for long range. And with the radio signal, instead of just, say, 10 meters for either Bluetooth or Wi-Fi, we can get up to 10 kilometers. And that means we could have the bins being detected anywhere on the school grounds. We'll be using an Australian frequency of 915 megahertz. And the network we're using is called the Things Network, or TTN. And it's part of a technology called the Internet of Things, where everything is interconnected. And you might be interested in that one of the local councils near the school actually does this. They're using this technology for the bins in public places. But for the school, and even if it was used by the public, we've got more than 9 bins to think about. So we'll also need to change that radio communications protocol. So that there's some of the issues. If you want to find more about LoRaWAN, go across to Wikipedia, and it's pretty well described there. The only thing, it's only meant for low bit rates. So it's not meant to transmit pictures or long messages. And here's the way that it would be wired up. So instead of using the Bitmaker shield for microbit, we use a special one, which is designed for the LoRaWAN, and it connects to our electronics that we used earlier. We now have all the hardware needed for the electronics and for the bin detection anywhere on the school grounds. But we do need a LoRaWAN gateway, and everything's on the internet when we do this. And if we look up the Things network, we can see the status of the bin. Okay, so for my references, I'm still using the Dahl book. So if you haven't purchased this, or if the school hasn't purchased it, it's a good idea to get a copy and understand how the basic circuits work, and see my simulations on the Tinkercad classroom. Plenty on electronics. So here are some of the references for that. And for the light emitting diode, an excellent tutorial is on the electronics tutorial website, where you can get an understanding of how these circuits work. For LoRaWAN, go across to the Wikipedia. And for my YouTube videos, you can get them here. Okay, that's enough for the time being. And see you next week, where we'll continue microbit and electronics.